So today, today about 50% is used for aerospace, and it's obviously widely used across all kinds of commercial goods. So this is what that titanium sponge looks like after it's produced. And so on the right is a close-up, right? On the left is a bundle of sponge that's probably bigger than me. And in the center is kind of a compressed pellet, if you will. So that sponge is what's considered pure titanium. It's not 100% titanium, but it's about as close as you're going to get. And that is what then goes on to the next step. But I'm going to skip that intermediate page to go here. So that tie sponge, if we were just going to make some commercially pure titanium, which is used for a lot of applications, then we would just take that sponge to an ingot. And basically, you're just pressing it, compacting it, and then it's going into a vacuum arc furnace. So it becomes an electrode. And that all that material is melted into a solid mass. So that process is usually 3 melt cycles. It's not just one melting and away it goes. It's actually heated, cooled, and it becomes an ingot. Now, we don't use a lot of commercially pure titanium in the bike industry. It definitely is used in a lot of industries for its corrosion resistance and such. But we're usually after an alloy, right? Because the alloy is stronger, we hope. So the process is identical. To make an alloy, you simply add the alloying additives at the beginning of this process, and in the end, you have an alloyed ingot. Okay. So if I back up one slide, this is kind of a cool look at the whole process. This is taken from the 1994 Bridgestone bicycle catalog. Okay, really cool. I mean, so much neat information was shared. 31 years ago? But basically, concentrated through the Kroll process, which they refer to the titanium tetrachloride as tickle. It's kind of a nickname, trying to make it sound like something sweeter than it is. Pretty rough stuff. Side note, it's also used in some special effects because it creates a really dense white smoke. It's also used in some military applications, the titanium tetrachloride, for that really dense white smoke, like if you're trying to block vision for an enemy, you can set up bombs with titanium tetrachloride, and create a really dense fog smoke. So there you can see it's a sponge, purifying sponge, compacting, electrode, vacuum arc furnace. Okay? So now you got this massive chunk of titanium that can be upwards of 10 tons. Typically more like 6 tons, somewhere in the 12,000 pound range for a titanium ingot. But that ingot is not what you're going to make. It's not ready to make a finished product. So skip that guy. So actually, I'll go back up. So these are those alloys that we see most common in the bike industry. And so 325, 3% aluminum, 2.5% vanadium. 6-4, I'm sure a lot of you have heard about 6-4. It's a wonderful alloy, extremely strong. same alloying elements, but just in different amounts. 6% aluminum, 4% vanadium. Okay. Really, the U.S. is the only region that calls it 325 or 64. Internationally, they're known as grade 9, grade 5. So, well, where's grade 1, 2, 3, 4, 7, 8? So there are many, many other alloys of titanium, and they're just not as common. They have more specific applications, and some are incredibly difficult to work with. But you can see the one major difference between 325 and 64 is that 325 can be cold rolled, cold worked. 64 cannot. So that's why you don't see it so much in bicycle tubing applications. It's just way more difficult to work with. Commercially pure titanium is also available in different grades, but those grades don't vary as significantly as when you start talking about an alloyed titanium. But you can see how different they are. The tensile strength of 325, about 105,000 psi versus 45,000 psi for commercially pure. Okay, so it's less than half. Let's see here. Cool. So obviously titanium used in a bunch of industries that require different shapes and sizes. So there's a lot of different processes to make solid, whether it's solid round bar, sheet metal, rectangular bar. Oftentimes it's rolled into 4 foot wide, 5 foot wide plates that are thick, just really diverse. Like any metal that we see out there, you can purchase different shapes and sizes: aluminum, steel. Very similar. Cool. So, what we tend to care about is tubing, right? We want to make a pipe. The ingots are processed to billet. Billet is processed to a tube hollow, and that's kind of the trickle down way of making a tube. So, if you're interested, I'll pass around some show and tell pieces. But that is a tube hollow, and you can imagine them like that's the tube that would be made from that. But basically, that ingot, because it went through that vacuum arc furnace process, sponge to ingot with those alloying elements, when it gets to this point, that is exactly what you're looking for. That's the alloy that you want. It's not going to change. That's going to be worked into billet, worked into tube hollow, and then worked into a finished tube. So from this point, the only thing you can do to the material is work it, cold work it, hot work it, anneal it, and heat treat it. And all of those processes, if they're done hot, need to be done in an inert atmosphere, because titanium wants to bond with some of the elements in our atmosphere when it's hot. So that's cool. So that tube hollow that passed around is what you would see on the left. And this process is called cold pilgering. And this is how you make a seamless tube. So you can see it's being drawn and it's being compacted by those rollers. And it has an inside mandrel, which is maintaining the inside diameter shape, tolerance, size. So this whole process is a forward and backward motion with a rotation. And you can see the tooling design on the right that it requires it to be incredibly precise, right? And I'm gonna send out a couple tubing samples. This is material that would have gone through this process. So cold pilgering, these are from Sandvik Special Metals, which is now, they're now under their parent company's name, which is Alima. It's a Swedish company. And this is exactly the process that those tubes undergo. And you can imagine it takes a while, right? And it takes a lot of control. But you can also see that it's changing the shape of that tube drastically, taking a heavy wall, tube hollow, turning it into a thin walled tube, whether it's an aerospace tube, something that's going to be used for hydraulic lines on a plane, or if it's going to become a seat post on your bicycle, changing shape drastically. So through that process, it's being cold worked. And that's why I'm sure if you've heard the term cold worked, stress relieved. That's a term it's most often used for titanium tubes that have undergone the cold pilgering process. So there's a lot of stress that's built into the tube that needs to be relieved, and that happens through vacuum annealing, and then maybe it'll go back into the pilgering machine again and get worked again. So it might run through this machine multiple times. Let's see. Yep. Okay. And this entire process, as it's called out there, is done cold. So it's done at room temperature, not a hot process. So, yeah. Titanium is prone to galling, which galling is, think of it as more or less like metal sticking to metal. That's why we use anti-seize when we install titanium parts and such. The same thing is true for material fabrication manufacturing processes like this, because the titanium is more prone to galling, it's more likely to stick to the tooling, which means the tooling has to be at an incredibly high hardness, incredibly precise, really high quality stuff. That's part of why it's so expensive. And this process is not possible with all alloys. Like I showed before, with 6-4 titanium, you cannot perform this process. At least not with traditional tooling. So, one thing I did want to talk about is there are 6-4 bikes out there. 6-4 tubing does exist and such, and a lot of it is a welded tube. So there's other people doing it, but one company is called Valley Metals out in California, and I've been out there and toured their facility. It's pretty interesting. They take a piece of sheet metal, 6-4, and basically they have some really long bending brakes, and they just incrementally bend it into, think of like an octagonal shape, till those edges come together. Once they're there, they do a full weld seam, and that was really fun to watch because it's a little kind of robotic train. It's like a train track, and the TIG welding machine is just sitting there. There's gas flowing, and it just follows along. And I think they were maybe 12 to 14 foot lengths. And then you end up with a welded octagonal kind of looking tube of varying diameters. Then that tube can be run through dies and becomes more and more concentric, and then eventually becomes a pretty round tube, but much, much different process. So budded tubing. So there's a number of ways to do it. Most typical, I think over the years, has been mandrel budding in the upper left there, where you have an internal mandrel that you put inside of the tube. That's usually a short-ish tube, like down tube length. And that is then pushed through a die, which forces the material to conform to the shape of that inner mandrel. And then that mandrel is removed. Now, what happens is, because you're looking for additional material on the ends and a thinner section in the center, that mandrel gets caught inside of there. There's no way to get it out. So that's a limitation to the differential between the wall thickness at the butt and the wall thickness in the center section. You know, you can get away with a certain amount of differential, but at a certain point that mandrel becomes stuck, basically. And there are some proprietary processes to remove that mandrel from the inside. Now, this, though, would be considered a cold work process. So you are going to build additional stresses into the tube through this process. And so it oftentimes will require that you start with an annealed tube, something of lower tensile strength, and then you work it, ends up a little higher strength. But if you start out with a high strength material, you might be putting too much stress into that tube, making it brittle and likely to fail. So that's why companies like Aura and companies like Reynolds, those are some folks that you can rely on for performing a good job. Machine budding you see in the handmade world quite a bit, and that's just literally turning the tube on a lathe. Typically, what you're doing there then is starting with a tube that is much thicker than what you would ordinarily start with if you were doing a straight gauge tube, and you're removing that material from the outside. This requires a little bit more of a little more precise turning equipment to maintain wall thickness through this process. You see this on examples would be like Firefly uses this process, and as well as others. They're not the only ones. External grinding can be done as well. That's basically the same idea. You're just removing material from the exterior of the tube. And then acid etch budding, kind of a unicorn because it's totally doable, but no one's doing it. It's just a really difficult process, but basically allows you to have an internally budded tube through the process of removing titanium with hydrofluoric acid. It was done years ago, but it's not done anymore. It's done in other industries to create like aesthetic finishes, but not for structural tubes. Cool. Right on. So the others, another important shaping process, you see this with like Columbus tubes, chain stays, seat stays. You see it from Reynolds, the tapering process. So this is done with a rotary swage tool. That's the machine on the right there. When I was working at Moots, we brought one of these Fenn swagers in-house. And oh my gosh, it is the loudest thing you ever heard. Because it's basically just beating. It's just a giant hammer. And you have these die that are built to the finished outside diameter shape that you want. So it's a concentric shape, right? But a taper. And you're feeding you're feeding the tube in, and it's just beating that tube to a smaller size. Okay, you can imagine that introduces a lot of work hardening. A lot of stresses are introduced into the tube. So you, again, start with a lower strength tube, finish with a higher strength, although you're not tapering the entire tube. So now you have a tube of varying strengths. This can be done with or without internal mandrels. Now this process, if it's done without an internal mandrel, all of that material is just compressed, and you end up with a very thick wall at the small diameter end, and then you have your starting diameter at the other end of the taper. So, but very common. Yep. And again, and this process is, from everything I've ever seen, is always done cold. So personally, right now I don't use any butted tubing or tapered tubes. Mostly because I really enjoy working with constant diameter tubes from suppliers that I know exactly what the condition of that material is, and it's reliable, and it works for me. So. Okay, so 3D printing, obviously this has been like the biggest news of the past 10 years, right? So I don't use any of it on my bikes. I do offer it as a seat post cap. I use it for only one part that I sell. So I'm not an expert on this topic, so I won't really dive into it, but I'll just kind of say, like, as I've seen it come up, it's really been the aesthetics of it that have kept me from using it and incorporating it in my bikes. I just don't care for that really rough finish. I think that, like, as somebody, I'm capable in SolidWorks. I can maybe use like 10% of its abilities. But for someone who's proficient in 3D modeling, like, the sky's the limit. So it's pretty cool stuff. It does tend to be quite expensive. So even comparing, like, in the center there, that the flat mount incorporated into chainstay, seat stay, and that piece right there is pushing $400, right? So compared to a dropout, that machine dropout that might be 100. Some flat mount inserts that are, I think on Paragon, they're like $12 or something. So less than half the cost, but quite a lot more labor to get to the same point. So it's a give and take, but it's really the aesthetics that don't turn me on. And I don't see the benefits in it for myself right now. I think that at some point, I know there's going to be a couple places where I'm going to really want to use it, so I probably will. Yeah, I've heard some feedback about ride quality. Just kind of a building up of stiffness in tie bikes that maybe is unnecessary. So cool. So why so expensive? So as you saw through those steps, just to get to the point where you have a tube set, a lot of folks involved, a lot of energy involved. Some of those like high titanium rich sands, they are limited. And then, of course, it is in high demand for special applications. So it's, when it's in demand, price goes up. We see that when the aerospace industry, when Boeing or Airbus kind of takes a dive, you see the price is very, very stable. When they're in high demand, you see the price start to go up in tie. I think not so much in the past few years, but 15 years ago, much more so. I think there's maybe kind of a settling of in the Thai industry and more abundance of it from Asia has probably changed that as well. Also, as a finished product, there's a lot of specialized tooling that's required. You'll see that through the next steps, but and also a high level of skill required for joining welding. So that basically covers getting titanium from the beach to a tube. Any questions regarding any of that? Any thoughts?
Well, you mentioned that you don't use butted tubing.
Mm-hmm.
Is that like less critical for titanium bikes as opposed to like a steel?
Well, butted tubings are used typically for ride quality, right? That's kind of the idea. And that makes a lot of sense when you're looking at steel and aluminum. So steel has the greatest weight over the greatest mass of those three. So removing that material has the greatest effect. When you look at titanium, you just don't have the same weight savings and, in my opinion, change in ride quality. Also, for building custom bikes, you're limited to stock butted sizings, which, sure, okay, that's why folks like Firefly are turning the OD of the tube. Then it allows 100% customizing the butt. However, the weight savings just isn't there for me, and the reduced durability of that tube just doesn't make it worthwhile for me. The movement towards gravel bikes has changed that as well, because now you're even more likely to throw a pretty significant rock into your down tube, and if that's been machined down 30%, it's going to be that much more likely to dent. So, yeah.
When you built the frame for me,
Mm-hmm.
I did the math on the butted tubes.
Yeah.
And so on a frame that ended up being around, I think, 1,450 grams,
Mm-hmm.
it was 80 grams.
There you go. So great example.
And,
Yep.
and the durability to denting and stuff seems
Yeah.
like a huge benefit.
Yep. So so a butted tubing overall, in my opinion, is a little less durable, right? And really that is kind of like the foundation of my bike building journey. Is I started building bikes because I broke bikes. And so I am somebody who's always thinking like, I want this thing to last, Yes?
Is there any difference in the process when you're taking a thick-walled hollow billet to a thin-walled tube? Is there any difference working titanium than compared to working chromoly steel? Or is it more or less the same process?
I believe, if I'm correct, I think there's just not as many intermediate steps. You can go more from imagine like the ingot or the large billet directly to tube.
In steel?
Yes.
Okay.
Yep. Because that's all hot.
Okay.
Hot forming. Yep. Cool. All right. Cool. So we'll jump into a little bit of love on titanium, right? So, this is kind of the way I look at it. Titanium offers the perfect balance of strength, lightness, durability, comfort, corrosion resistance, allowing for a custom bike that lasts longer, rides smoother, and requires less maintenance than both steel and carbon fiber. So, titanium is pretty amazing. Again, back to those alloys compared to commercially pure titanium. Titanium that's alloyed like the 325, its corrosion resistance is even greater than pure titanium. Pretty impressive. You drop that road bike into the ocean, pull it out in 500 years, and put the latest Durace on it and go for a spin, right? I know we're not all going to last forever, but I do like the idea that bike might ride on beyond me, as opposed to being a disposable bike. Back to durability and the lifetime of the product, but also the ride quality. So titanium has a pretty amazing modulus of elasticity. And that's kind of what balances the performance and the comfort. It allows the efficient power transfer, but still being flexible, and absorb vibrations from the road, gravel, asphalt. One of the best places to go test a titanium bike is like a road with expansion cracks. If you're familiar with that, pavement separating. Those kind of really abrupt shocks is where you really notice the difference in a tie bike versus honestly any other material. I mean, steel is pretty amazing, but tie is definitely, in my opinion, something special. Also, the weight to strength ratio is super attractive. It's as strong as steel and about 45% lighter, and it's twice as strong as aluminum. It's about 60% heavier. So pretty amazing material. Obviously, I build custom bikes. It lends itself to customizing, I think, because it's most often, like I said, available in straight diameter, straight gauge, many different diameters, many different wall thicknesses. So you can really play around with a lot of different shapes and sizes of bicycles with titanium.
Are your forks titanium too?
No, the fork being an unbraced structure hanging out there in space, definitely carbon fibers strength, stiffness is pretty amazing in that application. But for a braced structure like the double diamond frame, I think titanium is amazing, allowing you to really feel that ride quality. And then, of course, aesthetics. So I think it's beautiful. It's kind of got that natural gray finish. That's you kind of see a titanium bike coming. I think it's really sweet. So that's why I fell in love with titanium. So construction process. Some shop stuff to talk about here, and go through it. So I don't have any, let me double check my mind. I don't have any hydraulic bending in the shop. So everything's done with manual, mandrel roller benders. That shot in the center, that is reality. That's for bending a 27.2 seat post for the layback. So you actually bend it into a boomerang, and then cut it in half, and you get 2 layback seat posts. I also use, like, if you're familiar with Cobra tools, their tube bender has a follow bar. That process works really, really well for titanium. But you can see on the right there, and you can see a bit on the left, that the mandrel and the roller, or the die, and the roller pretty well capture the tube, right? And that's important through this process. With titanium, it's very high strength. It's a pretty low diameter to wall ratio, and so you really need to capture that tube and maintain shape as you're bending. Shaping is all done, for me it's all done in-house. I don't bring in anything that's shaped. So on the left you can see manipulation that's happened to a batch of chainstays, and in the middle there that's that's a hydraulic press for shaping. So I've got a whole drawers full of different tooling for creating those shapes and bends. On the right, is the chainstays on the mountain bike that I have in the booth. So if you're curious to kind of see what some of that shaping looks like, I'd consider that fairly extreme shaping in those mountain bike chainstays, but works out really nice.
Were you using the middle picture die to form the dimples
On
in
the right.
picture?
Correct.
Okay, gotcha.
Yeah, yeah. And don't worry, I have since repaired the the die in the center there. You can see it's like bowing. That hydraulic press is pretty powerful. So titanium loves to be turned, which is a pretty cool thing. What you're looking at here, the left is on my little lathe, and the center is a Morisaki. It's a pretty big lathe. It's a 17 by 40, and it just rips. It just loves turn and tie. So that comes down to lower chip load. So that's something when you're working with titanium, you don't want to load it up trying to take a huge cut of material. But if you have a nice chip load, like single point tools, you can turn it all day long. It's just a total joy to turn on the lathe. That's me at 18 or 19, turning some titanium back in Oregon, trying to make some titanium crank arms, which I brought an example of. So turning works out really awesome. Milling and drilling, all done with really pretty typical tools, knee mills, horizontal mills. But what you run into is that what I just said about chip loading. If you're trying to end mill and you're taking too much material, you better have a super rigid machine, and you better have full-on coolant going. If you're doing everything manually, you need to be taking pretty light bites, and and running fairly sharp, high-quality tools.
Only carbide, or have you gotten away with high-speed steel cutters?
Actually, I find that a lot of high-speed steel cutters work really, really good
Because they're sharper?
because they're sharper.
Okay.
Yep. And also, I feel like I'm not a trained machinist,
Yeah.
but I was trained. So I didn't take it to the nth degree, but I had a lot of training. And you can get away with a lot with a high-speed steel tool. Also, I don't feel nearly as bad breaking a $35 high-speed steel tool as a $120 carbide tool. Yeah, big difference. I do have a couple operations though where I maintain specific cutters for those jobs and don't use them for anything else because I don't, because they're $200 end mills that I don't want to trash.
Yeah.
Yeah, cool. So milling, so mitering and coping, right? That's all about bringing the round tube to fit up against a round tube, right? All done with hole saws. So you've probably seen pictures of it being done. The picture on the left there, those are some French ultra hole saws. If you can find them, use them. Buy them, use them. They're awesome. In the middle are some made in Germany. That's from Rock Hard Tools. Both of those are a low tooth per inch. Apologies. High tooth per inch. So those are 10 teeth per inch. And that's what you're looking for you want to be able to take these lighter cuts more frequently. The hole saw on the right is a Starrett, which is a 6 tooth per inch. Not using them nearly as much anymore these days. Gone almost exclusively to the lighter ones. And that goes for most materials. When you have a thin wall and you're trying to cut it, you really don't want a high chip load. You want to reduce that chip load. You can reduce it by thickness of the cutting face or number of teeth as well. So, but very, very straightforward process. You can see, tubing is just being held in V blocks. The one on the right there is actually a custom tooling setup that I designed and built for my seat posts that allow me to do custom offsets from 0 to 35 quickly without adjusting the machine whatsoever. I just adjust the tooling. Yeah. So there's that coping. So sanding and grinding, typical stuff. Aluminum oxide belts for cleaning up miters. Titanium. We'll get into the welding just a little bit, but basically all surfaces you want to remove that very, very slight oxide layer that occurs. And so you're using, whether it's a 3M unitized wheel, which is like a dense Scotch-Brite wheel, or like a 120, 180 grit flap wheel for the inside diameter. You're cleaning up those surfaces before you weld. So that's what it looks like in the welding area. Yeah. Yes, sir.
For tapping, do you just
Oh.
use standard uncoated taps?
It depends on how much I care about what I'm doing. But the OSG coated are typically the best. The 3-flute. Yeah, only buy good taps. If you're working on a finished product, right? So we're only depends on what you're doing, but oftentimes you're working on a finished product, so you've already got 25 hours into it. The last thing you want to do is screw it up with a tap. So, use high quality taps. There's a number of lubes out there, but also tapping, pecking, in and out, cleaning it up. If I'm chasing or finish tapping a thread in a frame, whether it's a rack mount or a fender mount or some odd thing, if it's the last thing I do, I might only tap a half turn out, completely clean it up, new lube, half turn, completely all new. Because the last thing you want to do is gall up that tap and break it off in there. And what's an extra 15 minutes, right? Tapping was actually on my list. So there's actually a couple other things I'll send out. There's a couple examples of titanium water jet cutting as well. So there's a couple other processes like I forgot to mention. So tapping, of course, high quality, plenty of fluid. The water jet cutting, if you're not familiar with that process, it's high pressure water that's shot out of an orifice, so incredibly high pressure. The last time I went down to the water jet guy in Berthoud, Colorado, he had just gotten receipt of a new machine, and he was telling me about the nozzle head, and I think it was a 4/1000th of an inch hole through the diamond head on the machine, and I think they were running 120,000 psi. And he was kind of showing me just some of the stuff they were doing. 6-inch aluminum, and just ripping. So pretty amazing, amazing stuff. But water jet cutting works on titanium really well. Unfortunately, there are particulates in that water. You know, you're not actually cutting it with the water. You're cutting it with the small particulates that are suspended in the water, and they do embed themselves on the surface of the titanium, so you can't go directly to welding. You can't take a freshly water jet piece and go directly to welding. It needs to be mechanically cleaned up. So sanding, buffing, prepping. And then also another process that's kind of, you know, I suppose I would call it like an old school process is EDM. EDM is electrical discharge machining. And if you're not familiar with that process, it's really, really cool. There's wire EDM and graphite electrode EDM. So I'll show you, I'll pass around an example of, this is a wire EDM for the square taper in the end of that crank. So that crank arm was made by me in 1996. And I credit that project as being really instrumental in learning a lot of the foundational pieces to building with titanium. But that wire EDM process is basically, you know, feeding a metal wire through a hole in a part and then spooling it and allowing it to run in a loop, basically, from spool to spool. And it's electrically charged, and the workpiece is in a bath. And every time that wire touches or gets close enough to the material, it arcs, and a tiny little particle of titanium is broken off. So to create the square taper in that crank arm took about an hour of the machine running. And then that wire EDM process it's used all the time in tool and die making when you want just incredibly precise tolerances in mating surfaces, just in any tool. But that wire position.